and I'm going to use the PDE to manipulate the energy functional's derivative so that I can bound it, right? So that's a little bit different than what you're saying, I think.
Okay. Okay, then basically differentiate with respect to time, and then manipulate the PDE. I mean, use the PDE to manipulate
Use
the.
the PDE to manipulate the integrand um, of the energy functional, right? And remember, the PDE that you get is going to be the completely homogeneous one, right?
Yeah.
You don't want to use the inhomogeneous PDE. So you want to say, well, V is equal to U1 minus U2. So then, like all the F's cancel out and the initial conditions cancel out. Yeah.
Okay.
So you always want to start with this, right? If you do what you're saying, you're going to get some energy functionals that you
Yeah.
can't
My,
really.
my only issue with that approach is, what do we do with f of x comma t? Because that will also be multiplied with ut, right?
No, well, that's the second thing I was saying, right? So if you have u tt minus c squared uxx is equal to f, right? What the way that you prove uniqueness, right, is you say, let's say I have u1 and u2, and these are both solutions to this PDE, okay? Then what I want to do is I want to show that v, which is u1 minus u2, I want to show that v is just equivalently 0, okay? So how do I do that? Well, I have to derive a PDE for v, right? And so when you do that, you have, u, also v, vtt minus c squared vxx, right, is going to be u1 tt minus u2 tt minus c squared, what is it, u1 xx minus u2 xx, right? And when you put this all together, right, this is all equal to f minus f, so it's equal to 0, okay? So the PDE for V is homogeneous, right?
Uh,
The initial conditions for V are homogeneous, right?
yeah.
This step is important, right? Is defining V and defining the initial value problem for V, right? Which I
Yeah.
think, yeah, I mean, I kind of went over it quickly in the lecture, but yeah, it should be in Shear and Levy where they go through that.
Okay, so this is the approach that we're supposed to take.
Yeah, so then you have this, and then you use the PDE for V, whatever it is, to manipulate this, right? So well, you differentiate dE dt, and you get something, and then you manipulate the integrand in order to bound it, basically.
Sure. Uh, Now, okay, so that's the approach that we take.
Yeah.
So just to reiterate, what you did was you defined the energy functional ahead of time,
Yes.
which is this, and then you took your PDE, and then you took V, and you took U1 and U2 as the two separate solutions that could potentially be the solutions, and then V is U1 minus U2, and we need to
Right.
show that V is 0. So if so we took V in the partial differential equation, but why did we take V in the PDE?
Well, because we want an initial value problem for V, so that we want to know something about V so that we can use it when we look at our energy functional, right?
Okay, yeah,
Because at the
and
end of the day, we want to show that V has to be equivalently 0. So the energy functional is relevant to V, right?
yeah, So
So it's a
define
way
energy.
of looking at the difference between two solutions and showing that that difference has to be zero everywhere.
Okay, okay. Oh, so define energy function in terms of V, not U.
Yeah, right.
Okay, okay. And then yeah, I'll give this a try. And then in question 4,
Okay.
we have so in class we had an integral for like the solution for Duhamel's principle had integral of f of ys d by ds, right? Where the integrals the limits are 0 t and x minus c times t minus s times and x plus c times t minus s for the solution, right?
Yep.
So
So yeah, that's Duhamel, right? So u xt is equal to the integral from 0 up to t, integral from x minus c t minus s, x plus c t minus s, and then we have this f of ys dy ds, right?
yeah, and then our f here is basically in terms of x and t, right?
Yeah, right. Yeah, so in problem number 4, right, your f of xt is what? It's sine of omega t cosine of x, right?
Exactly. So
So
how
your
do
f of ys is just going to be sine of omega s cosine of y.
but why did we take y for x and s for t and not the other way around?
Um, well, that's just those are the dummy variables that we chose for the x and t directions. Um, I mean, so we're just asking how that comes about. I mean, so here, right, these are the limits of the y integral, right? These are x coordinates, right?
Yeah.
You have to choose a dummy variable because you can't use x again because you're already using it on the outside here. And then we need to integrate in time. So these are the time coordinates, right? So those are integrated. That's our s is like our dummy variable in our t coordinate.
Yeah. Okay. That's right. Okay. And the second part was a bit more difficult to understand. Like
So I mean, you're just saying are you saying
the
problem 4 is hard?
yeah, like the second the limits of the second integral x minus c times t minus s and x plus c times t minus s, that's much more like how do we
Well,
interpret
yeah.
that?
So this is just the domain of dependence, right? So this is just how you define it. So if I have, this is some point xt here, right? And then I can think of this as going, this is my s or whatever, and this is my y here, right? And so
Oh,
these limits are just corresponding to a point. They're just points along this triangle that
okay.
determines the domain of dependence, right? And so what is this line? This is just a characteristic, right? So the way I can define it is as x. Let me make sure I get this right. I don't want to mess this up. But yeah, so this is my x plus c t minus s, and this is my x minus c times t minus s, right?
Yeah.
And in each of these s values, it's just a different value of t or whatever. So this is, that's integrating here, and then integrating in this direction in 2D, that's this inner integral, right? So at each point in time, I'm integrating, in x that way, and then I add up all those integrals by integrating by in the time variable.
Oh, okay. That makes sense.
So it's a way of defining that integral over a triangle, right?
Yeah.
Whenever you do these whatever x, y, or I mean here it's like an xt integral, you have to parameterize the boundary in one dimension by the variable that you're integrating by on the outside.
Yeah. Yeah. I remember doing this in undergrad. Yeah.
Yeah, yeah. So it can help to draw pictures sometimes, right? I
Yeah.
mean, I think it's much clearer when you see the picture here and you think, okay, well, how do I define this? You know, how do I
Yeah.
define those lines in the right way?
Yeah. And my third question being, so I didn't properly understand the problem uh, in the last homework. In the last homework in wave equation, we had a question that was related to the D'Alembert solution, right? 4.1, I think.
Okay. Yeah, I remember that one.
So yeah, I mean, I just wrote something just to get some points, but I wasn't sure how to go about the problem.
So just the whole thing didn't make sense, or